So we now talk about magnetic force between two parallel currents. So say you have two long wires, wire 1 and wire 2. These wires are separated by a distance d. So wire 1 is carrying a current of I1, wire 2 is carrying a current of I2. Now first focus on wire 2. So wire 2 will create a magnetic field, and you can find out this magnetic field by the right hand rule for magnetic field, and you will see that the field goes around like this. This goes around like this along the wire. So at a distance d, this field B2 is acting downwards, as you can see the direction on wire 1. In particular, it is perpendicular to wire 1. So wire 2 creates a magnetic field B2, and this B2 is perpendicular to wire 1, as we have just talked about. So the magnetic force on wire 1 of length L, so you fix a length L, say you have this length L, and as you know, the length vector points in the same direction as the current. Then the magnetic force is given by this formula. F1 vector is equal to I1 times L vector times the magnetic field vector. So in terms of magnitude, we will have F1 becomes I1L B2 sine theta. And we have just talked that this theta here is 90 degrees or pi by 2 radians. So you say sine theta becomes 1. So this becomes F1 becomes I1L B2. Now our first application of Ampere's law was about a current carrying wire and its magnetic field, and we found out if the wire is carrying current I2, the magnetic field at distance t is given as mu naught I2 divided by 2 pi t. So this was the magnetic field at distance t from a current carrying wire I2. So now notice the direction of the force. So force is perpendicular to both the length and the magnetic field, obviously because it is a cross product. And then you can see going from length to magnetic field, we are going clockwise, and the force is acting now in this direction. So you can also use your right hand thumb rule to find this out. So current carrying wire I2 in this direction creates a force F1 vector on the wire 1. Now we can do the same analysis on wire 2. So what would you do? You would first compute the magnetic field set up by wire 1, and from that you will again take a cross product and compute force F2 vector on wire 2. So F1 vector is here, so suppose you are going to compute the same thing on wire 2, you will get F2 vector like this. So both these forces are attracting each other. So notice that the direction of the current is same. So I1 and I2 are flowing in the same direction. The wires will attract each other. So as just shown by forces F1 and F2, which I have just drawn. Now if you reverse the current, so say you reverse the current in one of the wires, you make this I2. Now as soon as you reverse the current, what will happen to the magnetic field? It will start going in the opposite direction now, like this. So this magnetic field will go up. So now we will have new magnetic field which will be going up here, and therefore the force would now act in opposite direction. So the force, new force would be in this direction. So if the current is reversed in one of the wires, the forces will now act in opposite directions, and therefore there will be repulsion. Now since the magnitude of force on both the wires is the same, so because that is the way the magnetic fields are generated, so the magnitude of force on both the wires is the same, so you can replace this F1 by F. So this F1 we can replace by F, and that is what we do. So we replace this F1 by F, you divide both sides by L, you get F by L is equal to mu naught I1 I2 by 2 pi d. So this formula is important because this gives us force per unit length. Gives us force per unit length. Now this is important because we can use this force per unit length to define ampere. So now let us define ampere. Now when the magnitude of force per unit length, so this is the per unit length, between two long parallel wires that carry the same current and are separated by a distance of 1 meter is 2 into 10 to the power of -7 newtons per meter, the current in each wire is defined to be 1 ampere. Now we want to define Coulomb. So when a wire carries a steady current of 1 ampere, the quantity of charge that flows through the cross section of the conductor, so suppose you have this long wire and it is carrying a current of 1 ampere, so the amount of charge that flows through here, through the cross section of the wire in 1 second, that is defined as 1 Coulomb.